In this video, we are going to start resonance. And resonance is going to be a really important concept in this course. Also in 236, resonance isn't going anywhere. We're going to use it over and over again. So as you're going through these videos, if you have questions on resonance, please make sure to ask. This is one of those concepts that if you don't really get resonance down, then it is going to be problematic as you go through the rest of the semester. So resonance. And the easiest way is to just kind of start with an example. So what I'm going to do is I'm going to draw our Lewis dot structure for nitrate ions. And if I was to go through all of the rules that we have for drawing Lewis dot structures from general chemistry, I would add up my total number of valence electrons. I would add 1 because of that negative charge. I would put the oxygen in the middle, and then I would attach everything with single bonds. The next rule said to put lone pairs on all of our terminal atoms until each has an octet. So I would do that. And I would end up with this. I didn't actually count the electrons, but I would be out at this point. I then have a problem because our next rule says that if everything that wants an octet still doesn't have one, we need to put in multiple bonds. And in this case, nitrogen only has 6 electrons. It doesn't have 8. So again, using our rules from general chemistry, I would need to take 2 electrons from one of my oxygens and then share it with nitrogen, putting in a double bond. And I'm going to take the ones on the top oxygen. But if I go back to that structure, I could have taken them from the left oxygen and had the double bond there. Or I could have taken them from the oxygen on the right and had the double bond there. And then we do need some formal charge. All of these oxygens that have the single bond and the 3 lone pairs do have a negative charge on them. So in general chemistry in 150 or 151, you would have been asked to draw all 3 of these structures. What we're going to add here is the fact that none of these are actually right. In general chemistry, you probably would have learned that they're all correct. In actuality, none of them are correct. What exists is a hybrid between all of these. So in actuality, again, I can't spell. None of these structures exist. Right, these are considered resonance structures. If I said draw all possible resonance structures for nitrate, there is actually one other, but these are 3 resonance structures. But resonance structures don't actually exist. What exists is a resonance hybrid. So the true structure is a resonance hybrid. And remember, the word hybrid just means it's a combination. So if I was to take all 3 of those resonance structures that I drew and combine them, I would actually have my hybrid. Right? If we look at those structures, right, remember that double bonds are stronger than single bonds, right? I have 4 electrons holding the 2 atoms together versus just 2. They're also shorter, and we can actually measure bond length and bond strength. And if I was to look at those resonance structures in the first one, I have 2 bonds, right, the ones I just highlighted in yellow, that would be longer and weaker than another bond, the one I just highlighted in orange. And that would be the same for all 3 of them, right? I would have 1 bond on all 3 of them that's stronger and shorter than 2 of the other bonds. But we know that that's not true. You can go into lab and you can measure bond length and strength, and we know that all of those bonds are equivalent. We also know that as far as the length goes and the strength goes, it's somewhere between that of a single and a double bond. It's not the strength of a single bond or the strength of a double bond, it's somewhere in between. So our hybrid, if we were to draw it, and I don't generally ask you to draw hybrids, sometimes they can be pretty tricky, but I'm going to single bond my oxygens. And then I'm going to put dotted lines in to show that it has partial single bond and partial double bond character. Those dotted lines mean they're partial bonds. And I can't really give it negative formal charge now. So what you would do is you would do like a partial charge on all of those because we can't show that formal charge. So, and often hybrids go into brackets. You don't have to have brackets. And again, I generally don't ask you to draw hybrids, but this would be my resonance hybrid. Right? I have some double bond character, some single bond character also, right? Those bonds are between that of a double and a single bond. And our word for this is we would say that our electrons are delocalized. And anytime you can delocalize electrons, it's actually going to be stabilizing. It makes things more stable when the electrons are delocalized. So the electrons are delocalized. So local means they're in one spot, right? If we d something, we're undoing it. So instead of having those electrons sitting in one spot, I've spread them out over the entire molecule. And the electrons I'm talking about are my pi electrons. We could put that in there, my pi electrons. So if I go back up and I look at these guys, right, my resonance structures, remember that double bonds contain one sigma bond and one pi bond. So the electrons in that double bond are pi electrons, right? Because they're in that pi bond. So I want a skinny highlighter here. Basically, remember my double bond again is made up of a sigma and a pi, and I'm just arbitrarily calling the one that I just highlighted in pink my pi electrons, my pi bond. It could be the other one. We're just drawing lines here. We would have to draw that orbital bonding picture to show it. But on my first resonance structure, it's in that one local spot, right? It's sitting right there between the nitrogen and the oxygen. My second structure, it's still localized, right? It's on the left between my nitrogen and my oxygen. And in my last one, it's still localized, right? They're sitting right there. Delocalized means I'm spreading them out. They're kind of there, and they're kind of there, and they're kind of there at the same time. So instead of sitting in one localized position, I've delocalized them. I've spread them out over the entire molecule. So my electrons are delocalized, right? And we said that that makes it more stable. Anytime in this class and in 236 or any class really that you have resonance, anytime you can delocalize electrons, you are making that structure more stable. In chapter 2, we're going to get into acids and bases, and one of the things that's going to make our acid more acidic is our base has resonance. Our base is more stable. So it's something that we're going to keep coming back to. So if I can take those pi electrons and spread them out over the entire molecule, it makes it more stable. Remember, chemical reactions are electrons, right? Nuclear reactions involve protons and neutrons, but chemical reactions only involve electrons. So if something is going to react, right, it's going to form a bond or break a bond, it needs those electrons to react with. So if the electrons are just sitting in one spot, they're easy to react. Right? If those electrons are not sitting in one spot, if they're kind of spread thin over the whole entire molecule, it's less reactive. Remember, more stable means less reactive. So instead of those electrons just sitting there saying, hey, look at me, come react with me, they're kind of spread thin, right? They're delocalized, making it less reactive. So what we're going to do in this section is we're actually going to learn to draw resonance structures. We're going to look at a molecule. We're going to be able to determine when it has a resonance structure and when it doesn't, because not all of them do. We're going to learn to draw those resonance structures. Even though resonance structures don't exist, they're still what we're going to draw. But we're going to keep in mind that what actually exists is this hybrid. Hybrids can be tricky. So we're going to draw the resonance structures, but then keep in mind that it is the hybridization. It is hybrids. And then also keep in mind, it makes it more stable, right? Our electrons are delocalized, stabilizing that molecule. It's less reactive when those electrons are spread thin. So how are we going to determine whether or not a molecule has resonance or not? So the first thing we want to keep in mind is that resonance structures involve no change in the order at which the atoms are connected. If I was to go back up and look at the 3 resonance structures that I drew for nitrate, nitrogen's in the middle for all of them, and it's bonded to 3 oxygen. If I was to switch how they were bonded, say I was to put an oxygen in the middle, it's not a resonance structure. So resonance structures are not isomers, right? We learned about isomers this week also. Isomers are things that are actually connected differently. These guys are not connected in a different order. So resonance structures involve no change in the order in which the atoms are connected. Right? They are not big O capital N-O-T. They are not isomers. One of the things I do test you on is if I give you a pair of molecules, I will ask you the relationship. So if I give you 2, be able to tell me if they're isomers. If I give you 2, be able to tell me if they're resonance structures. If I give you 2, be able to tell me if they're just playing the same thing but drawn differently, because I'll do that. Right? So these guys are not isomers. If carbon's in the middle and it's bonded to 2 oxygens and a hydrogen, then in its resonance structure, carbon's going to be in the middle and it's going to be bonded to 2 oxygens and a hydrogen. So we're not changing how they're connected. The only thing that's changing are our lone pair electrons, so non-bonding electrons, and pi electrons. So it's just an electronic reorganization. So resonance structures involve a change in the, that's supposed to say in the, sorry, in the electronic organization. So what that means, we'll give this one the asterisk with a circle around it, only the non-bonding, so our lone pairs, and pi bonding electrons have changed. And when I say change, we have to have the same number. We can't, like, if we had 4 pi electrons and now we just get rid of electrons, that's a change. It still has to be a valid structure, so we're just moving them. So the only thing that's different are where our lone pairs or non-bonding electrons and pi bonding electrons are. Again, if we scroll way back up and look at those resonance structures for nitrate, the only difference between them are where the lone pairs and that double bond, right, my pi bonding electrons are located. Those are only going to be our changes. So only the non-bonding and pi bonding electrons have changed. And then just a couple of reminders. I know I've said this recently, but it's really important. Reminders. We draw the resonance structures but it's the hybrid that exists, not the structures. And then I'm also going to put this on here. We're actually going to show how we get from one to the other. We're actually going to draw arrows showing electron movement. And again, because the structures don't exist, that electron movement doesn't exist neither. So a lot of times people like to think that the resonance structures are in equilibrium with each other. They're not, because they don't exist. So resonance structures are not in equilibrium, EQ for equilibrium, with each other. Right, again, it's the resonance hybrid that exists. It's just often really difficult to look at that hybrid. It's hard to draw it. So we're going to draw the structures. We're going to show how we get from one structure to another, right? But we're going to remember in the back of our heads or in the front that it's not actually what happens, right? What actually happens is it's the hybrid, the delocalized version, not the localized versions that we're going to draw. And then again, remember, I'm not connecting them differently. So they differ only in the arrangement of the electrons, not atoms. So resonance structures differ only in the rearrangement of electrons. That was the electronic organization that I had set up above, not atoms. So I'm not moving atoms around, I'm only moving electrons around, right? And the electrons that I'm moving around are my, are my non-bonding and pi electrons, right? I can't move around my sigma electrons, right? If I was to do that, then I'm actually breaking the bond. My single bonds are made up of sigma electrons. And because I can't rearrange atoms, I can't rearrange sigma electrons, only pi electrons. So electrons in those pi bonds. Okay, so let's do some. So the way, if we're going to have resonance structures, we need two things. I need to have electrons I can move, and then I have to have a place to put them. So I call them electron sources, those electrons I'm going to move, and then an electron receptor, the place I'm going to put them. So we must have, if we're going to move them, electrons to move. And this is how my organic instructor called it ages ago, and I still use the word. We must have pushable electrons. Basically, electrons we can move. Whenever we were doing electron resonance structures, she would say push the electron. So we have to have electrons to push. We can only push them if they can move. So they have to be lone pairs, right? Non-bonding electrons or pi electrons. And then we have to have a place to push them to. We have to have a place to move them to. So we have to have an electron source. These are our pushable electrons. And those are either going to be a non-bonding pair, so a lone pair, or they're going to be pi electrons. Remember, those are the only things we're moving. We're not moving atoms. And then we have to have an electron receptor. We have to have a place to put them. Right? A place to move the electrons to. And that can take place that can be a couple different things. So an atom with a formal positive charge an electronegative atom, so something like oxygen, sulfur, nitrogen, and then an atom that has pushable electrons on it itself. So you can actually move like two sets of electrons. You can have your original source, and then you go and move them onto an atom that has electrons that you can displace, electrons that you can move. So an atom with pushable electrons. And hopefully this will make more sense when we do some examples. And then this one's also super important. The electron source and the electron receptor must be adjacent. You can't be leapfrogging atoms. So these guys need to be next to each other. So just because you have a source and a receptor doesn't mean you have resonance. The source and the receptor must be adjacent to each other. So we have to have electrons we can move, we have to have a place to put them, and then they have to be neighbors. Couple other things, I guess one for sure, the net charge on all resonance structures is the same. So if one of your resonance structures has a net charge of a -1, then all of your resonance structures need to have that same net charge. Now I'm using the word net because you can get a -1 net charge a few ways, right? I can have one atom that has a -1 charge. I can have one atom that has a positive charge and two atoms with a -1 charge. It would still be a net of -1. I can have an atom with a -2 and another atom with a +1. There's different ways to get that. So I don't have to have the exact same formal charge, but when I add those formal charges together, the net charge needs to be the same on all of my atoms, or on all of my structures. So some examples. I think that's probably the easiest way to go here. So I'm gonna draw, actually let's do it with skeletal. And if you're not seeing it, we can draw it back out. So since we did learn skeletal structures, this is good practice. So I have this. So the first thing we want to do is we want to say, okay, do I have an electron source? I do have a pi bond, so yes. Do I have an electron receptor? I have a formal positive charge on that end carbon. Are they adjacent to each other? Yes. So this molecule would have resonance. Just to make sure everyone's seeing, I have two hydrogens here. I have this, because it has a formal positive charge, how many hydrogens are on that carbon? Yeah, hopefully you guys came up with 2, right? Carbon with a formal positive charge only has 6 electrons on it. Right, 4 minus 3 gives me that +1. So this is what the one on top looks like. So yes, this would have resonance. So the way we're going to draw the structures is we're actually going to show electron movement. So we're going to add curved arrows. So use curved arrows to show electron movement. And that arrow is always going to go from the electron source to the electron receptor. It's showing where the electrons are going, not the other way around. So it always goes from the electron source to the electron receptor. If you draw your arrows in the other direction, you are going to lose points. So we want to show where they're going. So from source to receptor. So use curved arrows from the electron source to the electron receptor. And then the other thing is we're going to put a resonance arrow which is actually going to be a single line with 2 ends on it. So that would be a resonance arrow. between resonance structures. So be careful, not an equilibrium arrow, right? An equilibrium arrow is two arrows, each pointing in a different direction. So we don't want an equilibrium arrow, we want a resonance arrow. So this is a new arrow for us. So one line, and then it's pointing in both directions. So my source, we're gonna go back up and we're gonna actually draw our curved arrows on this one. My source is that pi bond, and then that pi bond is moving to that atom that is non-octet. So I'm gonna show the electrons moving there. I did my arrow on top, you could have done it on the bottom, right? I could have done this, that's fine. I just need to show them going from that pi bond over to the other side. I'm gonna add my resonance arrow, and then I'm gonna draw the structure that we got. So what I did, let's use our highlighter here, I took these yellow, right, my pi electrons, and I moved them over here, not that that's supposed to be an arrow. I moved them over there. So what it's gonna look like is this, and I now have a formal positive charge on that side. It might be, since you're still learning skeletal structures, we'll draw it out down here. So that carbon, that sigma bond is still there. Those hydrogens are still there, right? We're not moving atoms. But I took that double bond again, right? I took those electrons, I followed that arrow, and I put them right there. So they're here. This still has its two hydrogen, right? We're not moving atoms, we're not breaking sigma bonds. And then when I do my formal charge calculation, this carbon has that positive charge. So the same thing as the one on top, just drawn out using structural formulas instead of skeletal formulas. I do like skeletal formulas just because they're so simple to draw, but when you're learning resonance and then you just learn skeletal structures, it's probably going to be helpful for you to draw them out. So I'm using kind of a mix of condensed and structural here. So remember, when I write CH3, those three hydrogens are bonded to that carbon, right? They're not bonded between oxygen and carbon because hydrogen can only ever have those two bonds. Or sorry, two electrons. So that's what this one would look like. So again, we're determining, does it have resonance? And then if it does, we're going to draw the resonance structure showing all electron movement and that resonance arrow between them. If it doesn't have resonance, then why is our question. So do I have an electron source? Remember, electron sources are going to be non-bonding pairs or pi electrons. So yes, right, I have lone electrons. I have non-bonding pairs. Do I have an electron receptor? No, right? There's no place to put them. I'm going to draw out that carbon because sometimes it's easier to see when you're learning. Right? And a lot of times folks will just draw something that's wrong at first, and you don't always notice it's wrong until you draw it. So don't be afraid to like get out paper and practice this, right? If I was to take these and I move them here, it's not always really obvious that you can't do that until you draw that out, right? If I do that, if you look at that carbon, right, I now have 10 electrons on it. And we can't do that. You can't have more than 8, right? We can have less, but we can't have more. So 10 electrons on carbon, big old sad face, right? And a big X. So we can't do that. That's not a possibility. If I was to take those electrons and move them over here, now I'm going to have 4 electrons on hydrogen, even a bigger sad face, right? We can't do that neither. So this one, while I have an electron source, I don't have an electron receptor. So no resonance. There's no place to put the electrons. right? You could just say no electron receptor. And I would be totally cool with that as your answer. So no resonance, no electron receptors are reason. Another example for us. CH2. Again, those two hydrogens are bonded to that carbon. CH, CH2, and then a lone pair on that carbon. If I was to draw this using a skeletal formula or skeletal structures, I would have this. There is, sorry, I forgot the negative charge. There is a negative charge on that carbon. So that's what it would look like. So these two are the same thing, just one in skeletal structures, one in condensed. And again, while you're learning it, it might be easiest to draw it out structurally. So my two hydrogens, one hydrogen, carbon, it's two hydrogens, and it's a lone pair. So good practice for drawing organic molecules. So all three of these guys are the same thing. So does it have resonance, right? The first thing we're looking for, does it have an electron source? And yes, I actually have two possibilities, right? I have pi bonding electrons, there's a double bond. And then I also have a lone pair. So both of those are possibilities. And then do I have a place that I can put them? I actually do. So this one does have resonance, and I'm going to draw it incorrectly first because a lot of folks do this, and I just want you, if this is what you're thinking, I want you to see why it doesn't work. In class, if I was actually doing this live, I would generally ask you guys, what do you want to do? And what I'm about to draw is what most people tell me to do. And I do it. I draw it on the board because we're learning. And like I had just said, you often don't know that it's wrong until you actually draw it wrong and then look at it. So a lot of folks say to take those pi electrons at double bond and move them over to the other carbon. And if this isn't what you're thinking we should do, then good, because this is, again, the wrong scenario or the wrong structure. But I just want to show you. So my resonance arrow, and then I'm going to have CH2. I now have a single bond because I moved those pi electrons. CH, I now have a double bond because I put those over here. And maybe you don't notice this right away because it's condensed. If we were to draw it out structurally, I would have a positive charge here, right? It's non-octet now. I have a double bond. I still have this lone pair, right? They didn't go anywhere, right? It was here. I didn't move it. I only moved those pi electrons. So that lone pair is still on there. And then I have that hydrogen, right? So these two are the same. It's just I drew the one out structurally. And again, if we look at this carbon, it has 10 electrons. And we can't have 10 electrons on it. So let's actually put the X through this whole thing. That's not what we want to do. So while I do have an electron source, it's actually going to be the other direction. It's going to be those lone pairs that I'm going to move and not the pi electrons. And again, until you draw this out and then take a look at it and be like, oh, 10 electrons on carbon, I can't do that, you're not going to notice that it's wrong. So don't just blindly move electrons and then draw your structure without looking at your structure. You would be surprised at how many people actually turn that in with 10 electrons on carbon. So we can have less, we can't have more, right? We can't have invalid Lewis structures, and that's an invalid Lewis structure. So what I am going to do is I'm actually going to take those lone pairs, that's going to be my source, and I'm going to move them in here to make a double bond. Now that's going to give this carbon too many electrons, so then I'm going to take these and I'm going to move them out onto that carbon. So remember, one of our receptors could be an atom that has electrons I can move. If I was going to draw the arrows on here, this goes in, this goes out onto that carbon. Make sure your arrows are pointing to the right thing. This is a really good point too. I'm gonna make this wrong again, and then I'll fix it. I actually will take off points for this. If you draw this and put the arrow on hydrogen, you're moving electrons onto hydrogen. We don't want to move them onto hydrogen, right? Hydrogen can't have those extra electrons, never more than 2. So do not do that, right? Electron goes from the source, these pi electrons, to the receptor, which is carbon. So just be really careful. The first arrow I drew, this one here that I'm making bolder, I'm actually making a pi bond. So I want to make sure that arrow is going to that bond because that's what I'm going to do. So my resonance arrow at CH2. Now the lone pair is on that carbon because that's where we moved them. Single bond, double bond. So that would be my structure. Right, if we add the arrows to this one, these are going here, so I have that double bond. These are going onto that carbon, so it has that lone pair. And then make sure you put your formal charge on there. Another example. So CH2, double bond again. CH, CH2, and then that carbon with the lone pair and a negative charge. So same sort of idea, right? Does it have resonance? If not, why? And then if it does, we're going to show all electron movement and draw the structure. So what do you guys think for this one? Do I have a source? I do, it's very similar to my last one. I have those pi electrons, and then I also have that lone pair. So I have two possibility for sources. Do I have a receptor? Well, it's similar to this one we just did, right? Remember, one of our receptors was an atom that has electrons that I can also move, right? An atom with pushable electrons. So if I go back up, these went in, and then these moved, right? I made two moves. Can I do that on this one? Yeah, I actually can't. This one has no resonance. I have a source. I have a receptor, but they're not adjacent. Remember, the electron source and the electron receptor needed to be adjacent, and I have this guy in the middle, and I can't leapfrog it. I can't take these electrons and move them all the way over to there, right? That doesn't work. So my electron source and my electron receptor are not adjacent. We can't do that. So electron source and receptor are not adjacent.